Hello everyone. Welcome to Python Challenge for All. Okay, so let's see what we're gonna do today. So today's topic is the title is playing with bits. Okay, counting 1 bit. So we're going to learn about the binary representation of decimals. Okay, any numbers. Um, I hope you know something about binary representation. Okay. So usually binary numbers are expressed using only zeros and ones, and we can express any numbers in zeros and ones by changing it to binary representation. For example, okay, let's see. Yeah, if you want to change 123 in decimal representation into binary, we can use bin function to change it to get this string representation of binary. So let's take a look. So today's topic is, let's see. So binary numbers. Okay. So for example, as I said, if you okay, let's check, write it this way. N equals 1 to 123. And if you write bin n, what you can get is the first 2 letters, 0b, it means that this is a binary string. And 1111011 means binary representation of 123. Good. How can we change this binary representation back to decimal? Okay, let's put this into B1. B1. B binary string 1. Okay, we can use integer function to change it to BS1, and we here as the second argument give 2 because this is yeah, binary expression is representation. Okay, binary representation, it will be like this. Okay, that's the same actually for hexadecimal. Okay, when you use hexadecimal representation, we use 16 symbols from 0 to 9 plus A, B, C, D, E, F. And hexadecimals are kind of expressed as 4 bits in one group and expressed by one symbol and chain expressed as this. So to do that, the same thing. We can change to hexadecimal. Hex n, we get 0x7b. We get a string 0x7b. 0x means that this is a hexadecimal representation, and 7b means 7 times 16 plus 11, meaning that, yeah, maybe we can calculate 7 times 16 plus b means 11. So what we get is 123. Okay. Again, if we want to change this back to number, so hexadecimal, okay, let's see. Let's sign it as hexadecimal string 1. And then we can change this back to integer by int hs1 and 16. This will get, we will convert it back to 123. Okay, good. BS1 and integer back. And here, HS1, integer back, 0x7b. Okay, so now we have a correct slide in which I say hexadecimal of 123 is 0x7b. Okay. Also, we have bitwise operations. Okay. So for example, there are not operation, and operator, or operator, and exclusive or operator. Not means that one will be changed to 0 and 0 changed to be 1. And means if answer will be 1 only if the two operands are 1, or is either of the operands 1, or yeah, that will be 1. An exclusive or is if only one of the operands are 1, they are 1. Like this. 0 exclusive or 1 or equals 0, 1 equals, these are 0, but these are 1. Okay? You can check yourself if you want by doing calculations as this. For example, we can try as n1 n1 and 2 equals, say, 123 and 76. Okay, in this way, we can write the binary representation for both by n being 1 and being n2. Okay, so they are like this. If we take, say, and, okay, so binary of n1 and n2, binary of n1 or n2, binary of n1 exclusive or n2. These will get, okay. So only when the 1 bit for both are 1, the answer will be 1, like this. Okay? The same for n1 and n2. They are all 1s. And exclusive or is like this. So please check it yourself that these constitute these corresponding operations. Okay? And also there are bit shifts. So this means shifting 1 bit, shifting by left, which is equivalent to multiplying the number by 2. This means that shifting it right by say 1 bit, which corresponds to getting the //2, dividing the by 2. And there is also possible to define assignment operation and the assignment operator like this. So for example, if we calculate, say, n1 by shifting by 1, we'll get 2, okay, we'll get, so n1a equals, and n1 by shift, we get n1a and n1a, which means this is a 1-bit shifted version of n1, and which means this is twice the number of n1, as you can guess. The same for left shift. For example, if we do the same thing for n1 and 2 n1, okay, n1b equals n1. And this time, how about 2? Okay, so n1b, n1b. So this was what we get, 2 bits right shifted the original number, this one, and which is equivalent to dividing it by 4. Division by integer, okay? If you divide it by 2, it will be 61. And if you divide it by 2 again, it will be 30. So this is what we get. Okay, finally, please enjoy yourself with these calculations. Finally, challenge the topic. Count the number of 1 bits in the binary. Okay, for example, in the case of 126, what we want to do is to get, as we see, 120, yeah, in binary representation of 123, we have 6 1 bits. So how can we count the number of ones in any binary number? That's a challenge. Please think about it for a moment. Stop the video and think about it. Okay, let's combine bitwise with right shift operator. We can calculate it. It's a bit confusing. Maybe you can try it next time. But easiest one is use count 1. Okay, so for example, if we have BS1, okay, BS1 is, if you remember, the binary representation for 123. So the easiest one is BS1 count 1. This will give 6, which is the easiest one to do that. But for more other way, please think about it, and we'll have the answer next time. Okay, that's all for today. Please come back next time. Bye bye.